Hello everyone, this is Shuangyan. I will show you our better enabling large-scale GNN training with batch-level graph partitioning. The graph neural network is showing outstanding results in improving the performance of graph-based applications, such as social network, communication network, citation network, routine interaction network, or roadmaps. Recent studies demonstrate that GNN performance can be boosted while using more advanced aggregators, deeper aggregation depths, larger sampling rates, etc. While leading to promising results, the improvements comes at a cost of significantly increased memory footprint, easily exceeding GPU memory capacity. To work around the memory bottleneck, a popular method is sampling. Reducing sampling rate might cause a loss of accuracy. Another method is distributed training, but it needs more resources. In this paper, we will introduce a method Betty to make GNN training more scalable and accessible while batch-level partitioning. Betty enables advanced and efficient GNN training with CPU and GPU memory. Betty is a transparent solution that does not require any hyperparameter tuning and preserve model convergence. Betty is open sourced. For the overview of the Betty, when we have a large input graph to do GNN training, we can decide the number of the partition while an accurate estimation of the memory usage. If the number of the partition equals 1, we can do full batch training without additional operations. Otherwise, we will construct the redundancy embedded graph REG to help to reduce the redundancy. After the k-way graph partition based on the REG, if the estimated memory consumption of the largest macro batch is smaller than the memory constraint, we can feed these macro batches into later GNN training process. Otherwise, we need to do the k+1 way partitioning until the estimated memory usage is smaller than the memory constraint. Betty introduced two new techniques, redundancy embedded graph partitioning and memory-aware partitioning, to effectively migrate the redundancy and the load imbalances issue across partitions. To achieve them, we need to get familiar with our batch-level partitioning design. It allows the model to train with a lower memory footprint without changing hyperparameters and convergence, transparent to the model training. In GNN, the input nodes feature usually take the largest portion of the total memory consumption. Batch-level partition reduces the input node feature in a macro batch. Different from GNN training, mini batch training in GNN has complex computation dependency on input and output label, make batch-level partition difficult. Batch-level partitioning has a basic ideas. First, partition a batch into micro batches. Second, calculate the loss gradients after each macro batch. Third, accumulate the gradients over consecutive macro batches. Last, update the parameter based on the accumulated gradient from the entire batch. Why the batch-level partition effective compared with traditional mini-batch training, Betty macro-batch training? Achieve the same convergence as the full batch training without any changes on hyperparameter or optimizers. Then construct a redundancy embedded graph REG to reduce redundancy in graph partition. This is an example to depict the node redundancy problem. We can see these different partition nodes will cause a different number of redundant nodes. The bipartite structure might cause high redundancy after the partition. That's why we need to construct IEG to minimize the redundancy, to transform our problem into a problem solvable by the traditional efficient graph partition algorithm, such as the Merced. From a large input graph, transfer to a smaller IEG graph, which only contains output nodes. In IEG, the weight on an edge is the number of the neighbors shared by the two nodes. The construction of the REG happens on CPU, and it is based on the binary adjacency matrix representation of the graph. The matrix C equals the transpose of matrix A multiplication with matrix A. Once C is generated, we further remove nodes that's not output and remove self-loop. The resulting graph is the final REG. With REG, we can apply any existing graph partition algorithm that minimizes the cut flow. Then we collect the output nodes to construct a list for partitioning and bipartite generation. During the aggregation stage, GNN would group nodes with the same integrity into one bucket so that the received message in a bucket can be processed as an dense tensor. The nodes whose integrity are larger than 10 are bucketed into the degree 10 bucket. When sampling fan-out size equals 10, we can see the number of the nodes of integrity 10 is the largest in figure A. In figure B, we can see a partition strategy can cause load imbalance, increasing peak memory footprint. Hence, integrity bucketing leads to the bucketing explosion and the partition imbalance. To minimize the effects of the partition imbalance, we introduce a memory-aware repartitioning algorithm that quickly decides the partition counts through an accurate estimation of the memory usage of a macro batch. Memory consumption of a batch in GNN does not follow a linear relationship, making it difficult to know ahead of time how many partitions are sufficient to reduce the maximum memory consumption to meet a memory constraint. Although it's possible to figure it out through try and error if a partition strategy does not prevent auto memory, it might largely waste a computation in a retrying process. Hence, we can do modeling and estimation of memory usage. The memory consumption is estimated by counting below items, such as the number of the model parameters, the total dimensions of the input features, and etc. The intermediate results of the aggregator depends on the aggregator we use. Here is the example of LSTM aggregator. Then is the evaluation part. The platform we use is Xeon CPU and NVIDIA RTX 6000 GPU. Each GPU has a 24 GB memory. The dataset we test are commonly used in GNN training. The GNN model are tested GraphSage and GAT. From this figure, we can see that Betty breaks the memory capacity constraint. With more micro batches, we are able to run GNN with more sophisticated aggregator, more layers, larger hidden size, and larger fan-out size. This figure shows the trend of the reduction of memory consumption and increase of training time as we increase the number of the batches. X denotes the number of the batches. The left y-axis represents max memory consumption. The right y-axis represents the pure training time without state movements. We can see that Betty effectively reduces the max memory consumption as the number of the batches increases, and training time increases as the number of the batches increases. But Betty is 36.4% faster than the mini batch training. In the left figure shows the convergence curves of the text accuracy for full batch training and macro batch training with 3 different number of batches. We can find that the model convergence is not impacted by the Betty macro batch training. In the right figure, when using 64 batches, Betty reduced the input load redundancy by 49.2% and 28.4% on average, compared with the best of 3 other partition nodes methods. For the key points to take away, first, unique memory access pattern and data structures in GNN calls for a new method to use heterogeneous memory. Second, Betty enables large-scale GNN training with large and complex graph on a single GPU without losing training accuracy and auto memory. That's all. Thank you.